Okay, so here we are at the review. If you are only using the PDF, it's hard to see that point between 200 and 250 there, right there, is definitely the red point. It wouldn't have shown up. So the first question says, find the percentile of the house represented by the red dots. You count all these to the left of that red point. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. There are 26 to the left of that, so 26 divided by, it looks like 40 homes, so 26 divided by 40. Get your calculator out. Escape. Okay, so 26 divided by 40 is 0.65. So find the percentile. It'd be the 65th percentile, which means that 65% of the homes are less than that home, which is 230,000, basically. Can't tell exactly what it is. Okay, calculate, interpret the standardized score for the house represented by the red dot. Okay, so I guess we have to figure out what that red dot is. Oh, so which sold for 234,000. Okay. So let's set up our z-score. So z equals 234,000 minus the average. So you have to average all of those. Well, fortunately, they gave us that, right? So 203,388 all over the standard deviation of 87,609. Okay, so 234, oops, minus 203,388 all over 87,609. That doesn't make sense. Okay, let's see what I did wrong here. 34,203. I think I see it. I think you have too many zeros there, right? There it is. I just mistyped it. Okay, so the z-score is 0.35. So calculate and interpret. So the house, the price of that house is 0.35 standard deviations above the mean. The z-score is 0.35 positive, which means it's above the mean. The same house sold 5 years earlier for 212,000 during the month which this occurred. The mean sales home price was 191,000. Okay, so we're basically saying let's do the z-score again. So the same house sold for 212,000, 212,500 minus, where the mean price was 191,223. It's kind of unusual, the same house, 76,081. So that one was 0.27 or 0.28 standard deviations above the mean. Which one sold for more money? I would say the first house. So the first sale was for more money. Okay. Kristen likes to, we're on number 3 now, to throw tennis balls to her dog, Bucket. Time it takes Bucket to chase down a ball, return to Kristen and drop the ball is equally likely to take any value in the interval from 8 to 15. So equally likely. So if you think about, let me try to get this, so I can get this just a second. So the fact that these are equally likely makes me think that this is a uniform distribution. And it says, so this is for number 3. It says from 8 to 15 seconds. So 8 seconds and 15 seconds, which means the distance between those things is 7 seconds. If the area under that curve, so that width would have to be 1/7, and the area, of course, is always 1. So we have the dimensions there. Draw a density curve. Be sure to include scales on both axes. So this is 1/7 on the way up and 8 to 15 there. Okay, so Draw about what proportion buckets will return the ball within 13 seconds. So within 13 seconds is like all of this, right? So that's 13. So that's a distance of 5. So 5 times 1/7 is 5/7. So whatever that is, as a decimal, type into your calculator, you get the answer for that one. What is the mean of the density curve in part A? So the mean of the density curve. Think about that one. Okay, so between 8 and 15, if you average those two, right, that adds up to 23. 23 divided by 2 is 11.5. So right in the middle is 11.5. Remember, that's the balance point. So 11.5 seconds would be the mean of the two. Okay. 5, density on Earth, 2.4. In 1798, the English scientist Henry Cavendish measured the density of the Earth several times by careful work with torsion balance. The variable recorded the density of the Earth as multiple of density of water. Here are their 29 measurements with a dot plot and numerical summaries of the data. Okay, so it's got all that listed out there for you. Is this data approximately normal? Let's look at the picture first. We're looking for 3 things. Is it bell-shaped? Is it roughly symmetric? And is it unimodal? So it's definitely unimodal. Bell-shaped, I don't know about that. And roughly symmetric, it doesn't look that symmetric to me, so I don't think that's roughly symmetric, so it doesn't look to be approximately normal. Based on the graph, so if you wanted to do the empirical rule to test that, you would take the mean and the standard deviation, right? So you would go in each direction here. So you take the 5.448 plus 0.221 and subtract that as well. So we've got some from 5.227. So I think 227 would be, or 22. So that's right here. And then 5.669. So that looks to be about there, I think. So you count how many are inside of there. And I think if you do that, you would probably get 23 out of 29. So then you would do the 23 divided by 29. So 79%. That's not too great, right? We're looking for 68%. You could probably almost stop and say this is not approximately normal. But two standard deviations, you multiply that standard deviation by 2, multiply that one by 2, you get those 2 values. And so now you're going between 5.006, so right there, that's like the second 2 standard deviations, and 5.89. Wow, so it looks like that's probably right there. So it looks like all but one. So I think there was 29 total, so 28 out of 29 I think would be, so 0.965. That's not too bad for the second one, but the first one was so far off, we really got no shot with this one. You go one more, it's 100%, and you can see it's definitely not approximately normal there. Okay, 7 has just installed a new automatic dispenser. The amount of ketchup dispensed follows approximately normal. Goal is to put between 1 and 1.2 ounces of ketchup. About what percent of the time will this happen? So it's a great use of the commands here we have, right? So we're going to go, let me bring this so you can see it. So we're going to go menu, 6.5, 2 is norm CDF. The lower bound looks to be 1. The upper bound is 1.2. Standard deviation is 1.05. And I'm sorry, the mean was 1.05. The standard deviation is 0.08. So it looks like I get 70.3% of the time. You also could have used, I guess you could have made, I don't know if the empirical rule would work there. That works really well, what we just did. So you're basically kind of drawing a sketch. I think 1.05 was in the middle. And you're going out 0.08, so 1.13, etc. You're subtracting 0.08, so 0.97, and so forth. And you're going from 1 to 1.2. So from 1, which is right around here, to 1.2 out there. Whoops. You're kind of shading that 1 to 1.2 area. And you're finding that in your calculator. And we think it's 7.73%, 70.3%. Okay, first let's figure out, we want 99%, at least 99% have between 1 and 1.2. Suppose manager. So I think they're saying, so at least 9 have between 1, so like 1 would be here, 1.2 way out here or something. And so that would represent 99%. Let me try this. So let's go inverse norm. So menu 6.5. Whoops, sorry about that. Menu 6.5.3 is inverse norm. So we think it's 0.01 to the left of that. The mean, I think, was 1.05. Standard deviation 0.08. Let's see. Okay, so I think I'm picturing it now. I had a little trouble there. So we've got a little left. This is a really tough question. Probably tougher than I would ask. So there's a little area to the right and left that forms the 1%. So actually over here, in this little area, is actually 0.05%. So less than 1% or half of 1%. So I think I would do that command in the calculator, but instead of putting 0.01, I would put 0.005, yeah, I think. Okay. But we don't know the standard deviation of 0.08. I'm going to try this one more time. Menu 6.5, this is a really tough problem. 6.53, it takes a while to think through. 0.005. We're going to default to 0 and 1. So this is going to be, okay, so we're negative, this value here is negative 2.57583. Standard deviation is below the mean. So we know that if you think about the z-score equation, the value minus the mean over the standard deviation. So we know the z value is negative 2.58. The value is, so we got to think. So between 1, so I want 1 on the left, so that's the value, 1 minus the mean of 1.1 divided by the standard deviation. So I think we got that equation. We can solve that using our calculator solve command. I think that'd just be probably easiest. Menu under a solve, negative. I'm going to grab that. I'm going to grab that number instead of retyping it. I might get it exactly. I like to do that. It's a nice move. 1 minus 1.1 all over standard deviation, which I'm just going to call x, comma, solve for x. So we get 0.038 fluid ounces. Wow, would be the standard deviation. Really tough problem there. Okay, so hopefully these are a little bit easier. Many professional schools require applicants to take a standardized test. So there's 1,000 students take such a test. Several weeks later, after the practice test, Pete receives a score. He got a 63, which places him at the 73rd percentile. This means that Pete did better than 73%. So I'm pretty confident that the answer is going to be D there. That's just kind of the definition of percentile. Closest to 28th percentile. So again, So 20th percentile, so we get our calculator figured out. We just did this a minute ago on a really tough problem. This one's much more straightforward. I might ask you this one, 653 or something like it. So 28th percentile means 0.28 to the left. So 0.28. What do you go z-score here, standardized score? So just 0.28 and negative 0.58. So we got that. Okay, 5 scores of the ACT score can be, okay, cool, with a mean of 21. So the ACT was that. What was Wayne's actual score? So we know the z-score was negative 0.6. It's considered z-score is the value we don't know, minus the mean of 21, standard deviation of 5. She's basically solving that. Totally fine to use your solve command, menu 3.1, stats class, not algebra. Negative 0.6 equals x minus 21 over 5. Don't forget to put comma x to solve for the variable you want. So 18 would be it. Figure shows a density curve. 7 values are marked. Which of the following statement is true? The mean of the distribution is E. So it's skewed left. I don't think that's true. Can't be true. The median is C. Now it doesn't cut exactly 50%. I don't think that's right. Third quartile of the distribution is D. That looks like the median to me. It looks like about half on each side. I don't think that sounds right. Area of the curve between A and G is 1. That is correct. I don't know if I got that right or not. 7 is D, yeah. Okay, 1965, the mean price of a new car was that, and the standard deviation, 2019. So we're trying to compare these, right? So the 65 we're going to do first. So Z equals, the mean price was that. $2,300. So 2,300 minus 2,650 all over 1,000. And then for the second one, which is the newer one, I guess. So we'd have 34,000. Wow, big difference in price. Minus 36,700. Standard deviation 9,000. So you get your calculator out. Type those guys in. Okay. Oops. 34,000. Yeah, that'd be nice if the car was only that much. I remember when I was young, a new Mustang was less than $10,000. I remember that. Okay, so which one? So that one was, so in 2019, the score is greater, the z-score is greater. So if you look at this one, the standardized score is greater than in 1965. Okay, 11 for your response. Okay, so find the 10th percentile distribution of body temperature. 10th percentile. Okay, so let's look at this. So there are 130 total of these things. 10th percentile would be 13. So there are 13 values below it. So we count out 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. So right there. That's the guy because there are 13 values below that. So whatever that number is right there is the answer to the question. The 14th value there seems to be 36.3-ish degrees. Michael's temperature was 37.5. Calculate and interpret Michael's standardized z-score. So z, again, is the value, which is 37.5, minus the mean, 36.805, divided by the standard deviation of 0.407. If you do that, I believe you get 1.71. So that means his temperature was 1.71 standard deviations above the mean. This distribution of body temperature approximately normal. Okay, so unimodal, roughly symmetric, bell-shaped, seems to hit all the bars as far as the graph, the look of it. But if you want to use the empirical rule, we'll have to, get the calculator out, do the mean, 36.805, plus the standard deviation of 0.407, then subtract that. So it looks like that'd be 36.39 or 36.4, right around there-ish, and 37.212. Always hard to tell here, somewhere in there. And so then, it'd be better if this was nicely labeled, a little bit easier to see. And you count them out in between those, and you get 97 out of 130. You type that in your calculator, and you get 0.746. Right away, we can tell this is not going to pass the mustard. We wanted 68%. I could fudge a little bit to like 69% or 67%. That'd be okay. But 75% is a bridge too far to travel. Again, you keep going with that. We already did one like that, so I'm going to stop on that one. Suppose I like this. We haven't talked about one like this. So this is part B. We're converted to Celsius. Find the mean and standard deviation. So using those means and standard deviations as our starting point, what's going to have to do? So the mean is going to be affected by both these. You're going to multiply the mean by that and add that to the mean to get the new mean. However, when you do the standard deviation, it is not affected by adding 32. So you're only going to multiply the standard deviation by 9/5 to get your answer. And you just do that in your calculator and you'll get it. Okay? Why did you do 12? I thought it was supposed to be 11. Okay. But that was a good one to do, actually. Okay, and last one. According to TrueCar.com website, the asking prices for cars for a certain model are approximately normally distributed. Okay, so, not a bad idea to draw it. 30, it's going to be hard to draw all that out there. But you're adding 607.5. And subtracting that as well to get the other standard deviations. The factory invoice price is $35,625. About have asking prices below that. So I know it's less than 50%, but that value is already to the left of there. So at this point, we're probably just going to get a calculator out. And so you're going to go norm CDF, and use 652. I like the default there of negative infinity. We're going all the way up to 35,625. The mean is 35,987. The standard deviation, I think they gave it to us, was 607.5. 0.275, so 27.5%. That makes sense. You're kind of sketching over there in 27.5%. According to TrueCar.com, the asking price is between 34. This car amount is considered good or great. What proportion of the cars have good or great asking prices? Okay, so you want, those kinds of prices when you get cars on the lower side, 652. So we want 34, 772, 36, 225. Mean was, I forgot, 35, 987, and standard deviation 607.5. 63% for that one. And the manufacturer MSRP for this model is at the 98th percentile. Okay, so now we're given this mean, the standard deviation, we want 98% of the data to be to the left of what value? So you're going to use the inverse norm command, menu 653, 0.98 to the left. I think our mean was 35, 987, and standard deviation 607.5. So hopefully that looks about right. Yeah, 37,234.7 be the answer there. Okay, that's your book review.